Hi everybody, welcome to Theory Lunch. Today we have Pedro Paredes who will tell us about some de-randomization.
Alright everyone, thank you very much for the introduction, Ryan, and thank you very much for all for being here, and also my speaking skills committee for evaluating my performance today. So first of all, I'd like to say that since I was organizing Theory Lunch for a year, I'm very happy to be able to stand here for more than 5 seconds. And today I'm actually going to talk to you about this new result on explicit near-Ramanujan graphs at every degree. This is joint work with Sahan Mohanty. He's a PhD student at UC Berkeley. He was an undergrad here at CMU. And Ryan et al., my advisor, of course, a professor at UC. So let's just jump right into this. And I'm going to start with very basic stuff. And I want to introduce these like things that I bet every single person in the audience know, but I want to make sure that we have consistent notation and consistent terminology for things. And also, as we'll see, I'm going to use this notation throughout the talk, and whenever I refer to any of these things, it's always going to be the same. So everyone knows what a graph is, so I don't need to say what a graph is. Of course, set of vertices and edges. We're going to talk about irregular graphs, so graphs where every vertex has degree d. And whenever I use d, it's always going to be the degree of the graph we're talking about. So if you see d, you know what it is. We're going to talk about adjacency matrices of graphs. So we're going to talk about adjacency matrices. So matrices where the rows and columns are indexed by vertices, and the VU entry is 1 if and only if there's an edge VU. Whenever there's an A, it's an adjacency matrix. And finally, this talk is also going to concern spectral properties of graphs. So we're going to talk about eigenvectors and eigenvalues. And so, of course, an eigenvector G with some eigenvalue lambda over an adjacency matrix A is a vector such that when multiply it by G, we get the same G but scaled by this factor lambda. And whenever you see a lambda, it's also going to be an eigenvalue. All right. Also, it's important to say that all graphs are going to be undirected, and they're almost always going to be unweighted. And if they're weighted, then they're going to be weighted in one particular instance, and I'll tell you about it when we get there. Okay, so very basic stuff. I'm also going to remind you of some very well-known properties about irregular graphs and spectral properties of irregular graphs, namely that because we're talking about undirected graphs, the matrix A is symmetric. So, of course, the matrix will have n real eigenvalues, and we can order them like this, lambda 1 being the largest eigenvalue, and then so on until lambda n. It's well known that the largest eigenvalue, lambda 1, is always equal to d in a irregular graph. And the corresponding eigenvector is the L1's eigenvector, and it's kind of obvious why that's the case. And some other facts that are well known is that G is connected if and only if lambda 1 is larger, strictly larger than lambda 2, and G is bipartite if lambda n equals minus d. These two last facts aren't super important. I just wanted to like sort of set the stage for what we're going to talk about. But the fact that lambda 1 equals d is actually very important. Okay. Now, the key property that we're going to talk about today is expansion. So we have a question already?
Yeah.
Yeah.
What if you took two complete graphs, or two graphs of regular graphs that were disconnected, like n over 2 vertices and n over 2 vertices?
Yeah.
What is the second? The first eigenvalue is d.
Yeah, the second eigenvalue is also going to be d in that case. If you look at the
Second, that's why it's not strictly less than.
Yes, exactly. Yeah, if you have to disconnect the irregular graphs, their larger eigenvalue for the two components is going to be d. So the larger eigenvalue is going to be d, and the second larger eigenvalue is also going to be d, because you can get a vector supported on like only only the vertices of one of the components or the other. Yeah. It's not like super important, but it's one of those things that it's kind of relevant for a talk, so I'm like mentioning it. But the key property that I want to talk about is this notion of expansion. And expansion is this, informally, is this property that tells us that sort of every small set of vertices has many edges on its boundary. And let's make this a little bit more formal and talk about combinatorial expansion. This value h of g over here, h of g over here. And the idea is that h of g is the minimum. This is a little bit cumbersome to say, but the point is this is the minimum for every subset of size at most half of the vertices. So we're talking about subsets of vertices over here. We look at the number of edges that leave this subset, and we normalize this by the total number of vertices in our subset. This is kind of cumbersome. You can look at this picture to see what this means. This means that if we have any set S of vertices, if you look at the neighborhood of the set, the vertices that leave S to outside of S, so not the edges that edges for S to S bar, so the complement of S. This subset that I call gamma of S is always scaled by this edge of G value. So this is like the minimum sort of expansion of any subset that is has at most half of the vertices.
What is E, capital E?
Okay, E is just the number of this is the number of edges from S to the complement of S. Don't look too closely to these. I'm gonna sort of throughout the talk show you some formulas and stuff. The formulas aren't super important. I'm just writing them because that's the formal definition of these formulas. And if you know about these things, then you can sort of interpret them. But I'll always give you a nice picture and a nice explanation of what they mean, and that's more or less what I wanted to retain from this talk.
When would you make the denominator the volume of S instead of S?
Well, we can make all sorts of different definitions. This is in particular is called edge expansion, and you can make different definitions. It's not super important what this is. I just wanted to sort of show a formal way of defining this property that every small set has a lot of edges in its boundary. But the actual property that I really care about is spectral expansion. So spectral expansion is simply defined as the maximum between lambda 2 and lambda n in absolute value. So the second largest eigenvalue and the smallest eigenvalue of our graph in absolute value. And it so happens that these two quantities, the spectral expansion and combinatorial expansion, are connected by different theorems and lemmas in your science and in mathematics. In particular, we know about this thing called Shiger's inequalities, a celebrated result that has many forms, and it's been known for a while, and even nowadays there's still work being done on different sort of forms of this for different objects. But the point is that these two, if the combinatorial expansion is large, then we cannot have the spectral expansion be too small. And vice versa as well. If our spectral expansion is small, we cannot have the combinatorial expansion be too large. The reason I'm talking about this being large and small, it's kind of unclear why, is it good or bad to have large or small expansion. But I'll tell you guys in a second why this is the case. So let's just understand that expansion is something to do with sets that whenever we look at the boundary of these sets, we see a lot of edges that leave our sets. And the point that I'm trying to make is that these two notions are connected, and we're actually going to focus on the spectral notion, so that we're going to focus on the second largest eigenvalue and the smallest eigenvalue. And we want this quantity to be small, and we'll see why in just a second. I'm also going to define something called a family of expander graphs. So an expander graph will be a graph that has some sort of good combinatorial or spectral expansion. And by family, I mean sort of an infinite sequence of irregular graphs, where the size of the number of vertices of our graphs is increasing. And for example, if we talk about combinatorial expansion, I want there to be some epsilon, such that for all i's, or all of our graphs, the combinatorial expansion is at least this epsilon. Or we can sort of define the same thing for spectral expansion. In this case, I'm going to say that there's some epsilon such that our lambda of gi, so this quantity over here, this quantity over here, is at most d times 1 minus epsilon. And the reason I place d times this thing is because we know that d is the largest eigenvalue because of what I showed before, and so we want this to be as small as possible. And I'll, again, tell you why in a second. Question?
Isn't this definition just one-sided expansion then?
This is two-sided because
sorry,
finding lambda is this maximum difference between these two things. Yeah. All right. So I'm still only sort of giving you a very overall view of these things. I'm going to make this a little bit more specific in just one sec. But so the goal of this talk is to explicitly construct families of graphs with good spectral expansion for all d. So this is a mouthful. So let's sort of deconstruct this. So I want to build graphs to have lambda g, so that quantity, the maximum between lambda 2 and lambda n in absolute value, to be as small as possible. And I'll show you in just a sec why this is a good thing. I want to do this efficiently, so I want a deterministic polynomial time algorithm that does this. All polynomial n, so they can construct these infinite families of subgraphs. So if I give you an n, I can give you a graph of size about n with these properties. And I also want to do this for all possible d's greater than 3. So all integers greater or equal to 3. Okay, so the question is, why bother? Why should I care about this? Question?
Why is
Oh, so we'll see in just a second why determinism is important, but that's a great question. And I'm actually going to answer this in the next 2 slides. And I guess the question is, why bother building these things? Why bother them being deterministic? Why bother doing them for all d? And well, I have a slide that I want you to ignore, basically, which is basically I want to show you that there's a lot of work that has been done and is still being done that uses expander graphs and these graphs with good expander properties to do all sorts of interesting things in computer science and math. I don't expect you to read this because, of course, there's all sorts of things here, but I actually want to give you one example. I want to go through an actual application that hopefully will answer this question of why determinism is important. And so I took this toy example from Huri, Lineal, and Wigderson, this really good survey on expander graphs from 2006. And this example is on RP reduction, error reduction. And so here's our setup. Let's assume we have some algorithm A. And we also have some binary language of binary words of length R. And our algorithm A sort of decides this language with some randomness. So our algorithm will take an element of this language, an element of the alphabet, or like the all possible words of binary words of length R, and also some random string of k bits. And then it will answer if it thinks that x is in L or not. And if x is in L, then our algorithm always replies correctly, irregardless of the random word that it gets. But if x is not in L, then for like a third of a fraction of these strings y, our algorithm is going to be incorrect. Another way to say this is that our algorithm is correct with 2/3 probability in case x is not in L, and if x is in L, our algorithm is always correct. Okay, so this is a classic example of an RP, the class, complexity class problem or algorithm.
So why is it like a witness to the...
Yeah, basically, yeah. You can think about this as like some machine where we feed like some x is our like the thing we want to calculate, and y is some set of bits that we can think about as our randomness, and our algorithm will pop out yes or no, and if x is in L, it will always reply yes, and if x is not in L, for a third of the strings y, it will reply actually, well, yes, and it should be no. Okay, so this is a simple thing. Let's assume we have this. And now our goal is how to decrease this error. This is a classic problem. How do we boost our probability of success, or how we decrease the error that our algorithm has? So what if we want to reduce this from a third to, let's say, delta? Okay, so I'm sure every one of you knows one simple solution, and the obvious solution should be, well, let's pick t independently at random uniform strings y through y1 through yt. And let's run A for all of these. Let's basically do t independent runs, where t is some parameter that we're going to pick in a second. And now if the result is 1 for every single run, then we just accept. Well, this new method, if x is in the language, obviously we're always going to accept, because all the runs are going to reply 1. If x is not in the language, then we're going to accept only if we get the wrong answer for all of the strings, all of the independently random strings that we get. So the probability of error is now boosted to a third to the power of t. So if you pick t to be like log something of 1 over delta, then we're good. And so actually, I'm going to do something. I have whenever I have this white box over here, you can think about this as a cheat sheet. I'm not going to really refer to it, but I'm going to have notation or terminology from past slides. So if you forget what delta was, well, delta was the target error from our algorithm that I just said before. So if you forget something, you can just look at this box, and hopefully whatever you forgot, it should be there. Okay. So I'm not going to refer to this anymore, but it will show up from time to time. Okay. So in this case, we pick t to be log 3 over 1 over delta, and we're done. We decrease the probability to delta. So this is pretty simple. Now, the question that I want to ask is, how many random bits do we need to do this? And this goes back to the question that you asked, is what if somehow we want to we save the number of bits that we use? We don't have access to a lot of randomness, because we can think that pure randomness is not that common or popular, or not popular, of course. It's not super, you don't have access to a lot of bits if you need a lot of random bits. So how many random bits does our refined algorithm need? Well, each run of our algorithm requires us to sample one of these strings y, and recall that the string y will have length k, so we need k random bits per string, and we need t total strings, so of course you need k times log of k times t, k times this thing that we just calculated. So if k is kind of large, then we need a lot of randomness. So my question is, can we use less random bits? Can we somehow save on the number of random bits that we use? And this is the fundamental question that concerns the area of, for example, pseudorandomness, where we want to decrease the amount of randomness that our algorithms use, because because we want to actually like just de-randomize an algorithm completely, meaning we want our algorithm to be deterministic, and that's sort of a complexity question between like that is BP equals to P, and all these like questions regarding are all deterministic algorithms, all randomized deterministic algorithms also just, do we actually need that randomness? Or we can just think about how can we use less random bits. We're going to use randomness anyway, but can we use less of it? Because we can think about it as precious or somehow. All right, so hopefully this is pretty basic, and now I'm going to try to show you how to do this if we have one of these magical expander graphs that I just mentioned. So let's suppose we have this strange object, this 2k vertex, the irregular graph G with lambda G being bounded by beta times D, where beta is something, like let's assume beta is some small thing, like 0.3 or something. So if you recall from the definitions from before, I'm saying let's assume that we have some 2k vertex irregular graph with some good expansion, some good spectral expansion problem. And we can say that it's good because beta is small somehow. Let's just assume we have this for now. And now there's some questions that arise here because, well, I just said that maybe k is large and we want to save on the amount of random bits, but then like if k is large and 2 to the k is super large, but let's ignore like time constraints or space constraints for now. Let's assume we're just focused on decreasing the amount of randomness that we have. There's a way of going around this problem, and I'm not going to go over it because it's not super complicated, but I don't have enough time to go over it. Okay, so our refined algorithm is going to be the following. For this graph, we're going to map every vertex of this graph G to one of these random strings y. So we can think about like each vertex is, for example, have vertex 1, 0, 0 or vertex 0, 1, 0 if k equals 3. So we have this bijection between vertices of this huge graph and random words y that we can feed to our algorithm. Okay, so now we have this bijection. Our algorithm is just the following. We start by picking some random word v1, or some random vertex, sorry, v1 from this graph, just uniformly at random. Now we're going to basically sample a length t random walk. We're just we're going to start, for example, here. We're going to pick uniformly at random one of the neighbors of our current vertex, and you're going to step onto that vertex, and just repeat this for t times. And t again is some parameter that we're going to pick in a second. And now basically for every vertex that we visit, because of this mapping between vertices and words, we're just going to run our algorithm A with our input x and this word vi for the vertex that we just visited. And again, we're only going to accept if all the runs were 1. Okay, so if you think about this algorithm, if instead of having this weird, like, nice expander graph that I just mentioned, if we had a complete graph, just a complete 2 to the k vertex graph, then we'd have the same algorithm as before, because every step we can go to any other random word of length k. So this would be exactly the same algorithm. And my point with this is that saying that somehow these graphs with nice expansion are sort of a way to approximate complete graphs but in a sparse way. I know this is like kind of like an imprecise statement, but the point is that I want to say that these expanded graphs are somehow good pseudo-random objects, and the reason why they're pseudo-random objects is because they sort of have this magical property that somehow approximate complete graphs. Okay, so why does this work? What's the error probability now? Okay, I'm not going to exactly show you why. I'm just going to sort of hint to you why this is the case. And the idea is that the problem, like if you think about this set view of all the words y where our algorithm fails for a fixed x, let's fix some x not in L, and look at this set B of like words that our algorithm fails on. Now the probability that all the VIs from our random walk are in B is exactly the probability that our algorithm fails. And we can prove that this is exactly bounded by third plus beta to the power of t. This is very similar to what we got before. We got a third to the power of t, now we got a third plus beta. Okay, so to prove this, you just need some this is a 2-paragraph proof, we're not going to go over it, but it's not very hard to use some linear algebra, and you can just simply prove this, as I said, in 2 paragraphs. But so the point is that now the error probability is this thing. So we get to pick t to be something like this, log of 1 over this thing of delta. Basically log of 1 over delta, similar to before. And now how many random bits do we need? Well, we need k random bits for the first vertex that we pick uniformly at random. But then we only need to pick a neighbor of the current vertex. So we only need log d bits for each run. So in total we need something like k plus log 1 over delta times log d. Which is much better if k is large. It's much better when we got before if k times log 1 over d, 1 over delta. So this is the point that if our algorithm is deterministic, we're saving on random bits over here because we just have this magical object that we deterministically constructed, this this expander graph. We'll get to Ramanujan in a second. This expander graph with this lambda g bounded by this thing. And now, because this is all deterministic, we only need to sample neighbors and we get this nice result. Okay. Hopefully this is clear. I obviously didn't go over a lot of details, but I just wanted to motivate you why having small lambda, small spectral expansion is a good thing.
So you only take one step.
What?
You only take one step of the random walk.
You take t steps. The point is, we take some random walk of length.
You need log d.
Log
You
d
take one
per
step.
step. Yes, per step you need log d. Yes. So we take log d times the number of steps, which is about, t is going to be about something like log 1 over delta, and we get this thing. Correct? Yeah. So this is not super important, but I really wanted to motivate why this is interesting, so that you guys can sort of understand why do we put so much effort into sort of try to get these graphs with like super small weight over here. Okay. So I'm going to start, now I'm going to sort of change gears slightly and tell you about how like these graphs with nice expansion have been sort of built over the ages. We started in, there's a lot of papers from like the 70s and 80s that do stuff like this. But I'm going to start by mentioning this paper from 86 where Nolan proved that a uniformly random d-regular graph has lambda 2, so the second eigenvalue of this graph, bounded by 1 minus epsilon times d, with high probability, for some universal constant epsilon. So this means that, so far, like I mentioned these magical graphs, but maybe they didn't even exist. Maybe don't even like, we can't construct them because they don't exist. This proves that they actually exist, and they are actually kind of, they actually are kind of frequent. Okay, so this was a like initial result. We're actually going to see a much stronger version of this in a second. Okay, so now in the same paper and in like some follow-up papers by Neil and Joel Freeman in '93, it was proven sort of a lower bound. You can never have lambda 2 to be too small. Lambda 2 is always at least this magical number 2 root t minus 1, which will pop up consistently in this talk. But you don't really have to memorize it. Just whenever you see something that looks like this is the magical number I was just talking about. Somehow, like, you cannot do better than this. There's some universal lower bound to this lambda 2 quantity. This is known as the Alon-Bopana bound, and this is very celebrated results as well.
There's no Bopana in the reference.
There's no Bopana in the reference, but I looked into this. Apparently, like, Bopana did some like preliminary work, and then the works of Freeman and Alon are sort of based on some of the things that they did. But that's a good question. And that's also going to be like sort of a recurring theme because there's a lot of things that are named after someone, but then like there's no papers. That person doesn't really have any papers in this area. But I guess that's just all matters.
Twice in this.
What?
And Alon appears twice.
Alon appears twice. Yes, that's true. Alon appears a lot of times. All right. So based on this lower bound, we're now going to define this magical word from the talk title. A Ramanujan graph is the regular graph. The regular graph G is Ramanujan if the lambda quantity G, this lambda G quantity, or lambda, the second or smallest eigenvalue and absolute value of the adjacency matrix is bounded by this magical 2 root t minus 1. And so a Ramanujan graph is basically a graph with optimal spectral expansion because we cannot do better than this. And so based on this definition, I guess this was defined in this paper by Lebotsky, Phillips, and Sarnak from '88, and some like parallel work by Margulies and some follow-up work by Morgenstern in '94. They proved basically the end result of all these papers was that for any d with d greater or equal to 3 and the d minus 1 a prime power, there is an explicit family of the irregular Ramanujan graphs. So there's an explicit, we can construct these irregular Ramanujan graphs, so graphs with this nice property over here, for any d with this weird property that d minus 1 is a prime power. They do this by looking at some Cayley graph of some finite, interesting finite group, and show that this Cayley graph actually has this nice expansion property. So it's sort of like a number theoretical result, and the reason this is called, they call it Ramanujan, is because those number theoretical results that they used to prove this property, to like prove the expansion properties of this Cayley graph, are based on some conjecture and some results by Ramanujan and other people. Okay, so I have a table here that I want to completely ignore. My point is, there were a lot of works since these first few papers that I just mentioned, LPS, Margulies, and Morgenstern, that sort of try to get this Ramanujan property for all d instead of just prime powers, d being a prime power, or d minus 1 being a prime power. And so there's like different things we can sort of optimize. There's a lot of like, different sort of frontiers in our area. Yes?
Yeah, so question about like domains of d that you're interested in. So at the beginning you said you're interested in d greater than or equal to 3.
Yeah.
And I guess like this explicit Ramanujan construction is also for d greater than or equal to 3. What is so special about 3? Like why are people not thinking about d equal to 2?
Oh, because if you have a two regular graph, that's just like a cycle.
Okay.
So
you're doing this part.
yeah, so only interesting cases are when d is greater than or equal to 3. That's a good question, but yeah, I should have mentioned that. But yeah, so we want any d, but yeah, for interesting cases of d. So as I said, I don't want you to like ignore this table. Like there's a lot of work that has been done on this kind of stuff, but I want to sort of show you now. I want to show you what we did, and that's like sort of it ends up being kind of better than everything in some aspect, and like slightly worse in some other aspects. It's complicated. I don't want to go over that. But the point is that we get something that's very, very close to the holy grail of this Ramanujan area, I guess. So what we do is, if you fix some degree d larger than or equal to 3, and some constant epsilon greater than 0, if you have some big enough n, then there's a deterministic algorithm that will construct a irregular graph G with about n vertices. You can ignore this 1 plus little of 1. It's about n vertices. It does so in deterministic polynomial time in n. And this time like is going to be this polynomial is going to be some function, and the exponent of the polynomial is going to be some function of d and epsilon, so f of d of epsilon. Doesn't matter, just polynomial in n, that's what we want to say. And finally that the lambda g, this spectral expansion of our graph, is almost optimal. It's going to be 2 root t minus 1, this magical number, plus this epsilon that we fixed. So we can get arbitrarily close to our goal, but just not exactly quite. So this is what we're going to do in this talk. We're going to I'm going to try to show you the main ingredients to achieve this theorem over here. Okay. Before we move forward, I just want to tell you about this sort of randomized result, which is the stronger version of the previous result that I showed you. Namely that if G is a uniformly random n-vertex deregular graph, then with high probability, we actually also already get this, like the second eigenvalue, or the second, and like the lambda, I'm just going to say lambda instead of just saying this countable. Lambda of G is bounded by this magical number plus some little o of 1 quantity, with high probability. Question?
What was the dependence on epsilon in the runtime?
The epsilon is somehow in the exponent of our polynomial time. It's going to be something like, it's some weird quantity like d to 1/4 times log d over root epsilon or something like that.
So 1 over root epsilon?
Yeah. I wanted to sort of like shove that under the rug because, yeah, it's not very pretty, but that's what happens in these kinds of things. But, well, as I was saying, so we have this sort of randomized result that sort of says, oh, another question.
Yeah, is there some value of epsilon after which you are basically indistinguishable from being Ramanujan?
Indistinguishable in what sense?
Like I could set epsilon to be like exponentially small in n, right?
You can't do that because if
I don't care about running time, let's say.
But if you don't care about running time, you can just sort of like try every possible graph and see if it's a Ramanujan or not. The real key thing is that being polynomial time is sort of important.
I guess we also don't know if such graphs exist.
Right, that's what I was asking. Like, does it imply existence at some point if you don't care about running time?
But I guess that's
no, I think yes.
You're asking if like you can show that such a graph exists. I'm not sure. I'm not sure about that. I guess that's still kind of an open question. I'm not 100% sure.
Doesn't this imply that they exist?
No, because this is plus little of 1.
No, but what about the MSS result?
The MSS is one-sided, right? So like you don't get lambda, you get, so lambda 2 is bounded by this thing, but it only does this. It only works for bipartite graphs. Yeah. But what you're saying as like is, this is also like plus something. We want to get like something that's strictly or like less than or equal to this thing over here.
Well, and I think the question was the way you wrote your last theorem, there was no lower bound on epsilon. It seemed like you could put epsilon whatever you wanted.
Well, the epsilon is on our coefficient. I guess, yeah, I see your point. There's some like things that I'm sort of ignoring here, but yeah, epsilon cannot be like arbitrarily small.
Yeah, because n depends on epsilon, right?
Yeah, so like, the running, but you're saying that like, well, if you only care about,
Yeah, fine.
if you only care about existence,
Right.
you could have like a super exponential.
Right.
It's unclear. I'll have to think about it, but I don't think this would quite. Get
Okay, so
that,
this
but
doesn't
that's
imply
another-
it straight away. That's
It doesn't imply it straight away. No.
Okay.
I'm like hiding some like details because that would be very cumbersome to mention here, but it doesn't imply it straight away. I'll have to like think about it for a second, but I don't think so.
So does the exponential construct, does the other randomized construction give you exponential graphs? For which that you can have generate something that looks like an oracle, you could still do random walks.
You mean like a strongly explicit type of thing?
I don't know what the word is.
Not quite. We kind of do that using this algorithm, so it's complicated, but the point is that using our thing, you can actually do this in the way you were saying, having like an exponential size graph with like an oracle axis to and neighbors of vertices. With we don't quite get that, but we get that like with high probability. Like with high probability, if you give me like a fixed like seed or random seed, you get the thing you were just saying. You can sort of construct this huge graph. With high probability, like the seed is going to be good enough.
You have a bold deterministic, and then you're using this word randomized.
Oh yeah, because that's a different thing. What I'm saying is this is deterministic. This construction is deterministic. But if you want to do this for like the exponential size thing you're saying, then you don't get that deterministically.
Okay.
Yeah. Okay. So hopefully now more or less everything is clear. Any more questions, I guess, before I move on? All right. So this result is very similar to ours. The point being that this means that with high probability, every graph is already basically good enough. Already has this property sort of that I just said over here. It's like arbitrarily close to 2 root t minus 1. So the goal is we want to de-randomize this result. We want to make this deterministic. And that's basically kind of what we do in this paper, is we sort of de-randomize this result, and it's not, and as we can see, there's some obstacles in our way, and my point is to sort of show you how we achieve this de-randomization. Okay, any more questions? All right. I'm going to start by talking about this thing called the configuration model. And this may seem like some side note on our paper, but it's actually very important. The point is, I'm going to sort of show you, here I just say uniformly random vertex irregular graph, and now I want to actually give you sort of a model of randomness to generate these uniformly random graphs that we can analyze. And this is called the configuration model. And the point is, we're going to start with n isolated vertices. And now we're going to have like I should say, my point here is, I'm giving you a model of randomness to generate deregular graphs. And I'm going to show you or sort of like mention that this is basically equivalent to being uniformly at random. So let's say we started with some n vertices, and now we have these like d f edges. You can think about them as like sort of sockets. Like these sockets are vertices, some like part of an edge. And now we want to sort of connect these f edges. Instead, we're going to have like a random perfect matching between them, and sort of connect them like every two sort of connect until we get like a deregular graph. Okay, so this is our model of random deregular graphs. And this is called a configuration model. I want to say that I don't want to like go into details here. This is very simple, but I'm not going to really explain it. We can also like alternatively think about this as like choosing some uniformly random permutation. This is actually very important. And this is just saying that it's like the way we pick our random perfect matching, we can think about it as some random permutation. Okay, just keep this in mind that our model of randomness is equivalent to picking some random permutation of a certain size, depending on n and d, and that sort of generates some deregular random graph with
Are
n.
you allowing is the sampling of the matchings with replacement, without replacement? Like, can you have parallel edges?
We can, yeah. So we can have parallel edges here. We can have self loops. So this is not like exactly uniformly random. But the point is that this is actually like this is contiguous to being uniformly random. So there's a constant probability that the resulting graph is actually simple, that no loops and no parallel edges. But we're going to ignore these details. It's not super important, so we can just assume that, well, our construction might construct some non-simple graphs. We actually deal with these things in the paper, and we actually construct simple graphs and show you how to do that, but I'm going to ignore those details here at the top. Okay, so back to our theorem that I just mentioned, and now I'm going to replace the uniformly trending irregular graph and say, if we draw G from this configuration model with irregular and n-vertex graphs, then the same thing as before applies. We're arbitrarily close to this magical d root t minus 1. Okay, so now I'm going to sort of tell you about some pseudo-random tools. We can think about, we have some sort of tool belt of sort of theorems and objects, pseudo-random objects that allow us to sort of approximate some purely random quantities. And so I'm going to sort of only tell you about this one that we used to actually do, and I'm going to tell you about the other next, but I'm just going to tell you this one in detail. So I'm going to define these things called delta ky's uniform bits. This is kind of a complicated name, but the point is that I'm going to first tell you the definition, and then I'm going to tell you what this actually means. Fix some delta from 0 to 1, and some k, positive k, integer. And now, if you have a set of n Boolean variables, and by Boolean I mean plus minus 1, such that for every subset S of these variables of size at most k, the expected value of the product of them is bounded in absolute value by delta. So what do I mean by this? What I mean is that this sort of approximates, in a way, a perfectly uniformly sequence of uniformly random Boolean random variables. So the point is that ky is independent Boolean random variables. So the point is that if I look at any k or less variables of this pseudo-random objects that approximates uniformly random Boolean random variables, they behave the same up to some factor of delta. So this is sort of a way of saying well, if I want to do this, and I want to sort of, if I need to construct, if I need some sequence of n uniformly random Boolean variables, but I don't want to use a lot of randomness, and we'll see why the randomness is important in just one sec. If I forego some of these conditions and say, well, I want to be almost there, I want to be close to that, and I want to be delta close somehow. If I only need this, then we're going to be good. So this is our definition. And again, this is basically an object that approximates sequences of uniformly random bits. And similarly, we can define the same thing for uniform permutations. I don't want you to read the definition stuff. This is sort of the same idea, but instead of approximating sets of bits, of ky's uniform sets of bits, we're now approximating sets of permutations of certain size n. So this is the same idea. We have some pseudo-random object that is going to be very close to the actual purely random object up to some factor of delta somehow. Okay. And so the point is that if we have these two definitions, we can actually construct these two objects. And there's a lot of stuff here that I also want you to ignore. They run in some time, they output some, and the point is that they're going to output some subset of the all possible plus minus 1 to the n sequences of random bits of a small cardinality. This is the point. You want to have a small cardinality of this set. And if we draw an element uniformly at random from this thing, we get this sort of distribution is delta ky's, this delta ky sequence of uniform bits. So ignore all of these polys and stuff. The same thing applies to permutations, but what I want to sort of point at is that these two sets have different sizes. The reason this is important is that, well, if we have something like this, and you want to randomize a certain result, if we have this object, when we use this sort of distribution, it's delta ky's independent or something, if we have this distribution, and we have some result that well, remember how our configuration model said that basically only this smallish random permutation? Well, if we replace that with some pseudo-random permutation, these delta ky uniform permutations, for some delta or k that we're going to see in a second, then well, if this is small enough, we can just run through all of the permutations in our set, and if we know that with high probability the the output of our, when we sample an element from this distribution, we get the nice condition that the spectral expansion is good. Then if we run through all of them, we're guaranteed that we're going to at least find one or many that actually have the condition that we care about. So our algorithm is basically, we de-randomize this way, and now if you run through all possible permutations, we are guaranteed to find one that has good spectral expansion, and we just do that by computing the actual eigenvalues of the matrix, and see, well, or the adjacent matrix of the graph we get, and see, well, is this good enough for us? Yes, then we're good. And then that's our algorithm. Okay, any have some questions? No? All right. Okay, let's make this a little bit more explicit. So our optimistic plan is going to be, we have this theorem that I've showed you multiple times, and our idea is, as I said, let's replace this confirmation model by, instead of using a perfect uniform at random permutation, some delta ky is uniform permutation for some k and delta. And now we try all the permutations from this pseudo-random set, so like that set that we have that we're just uniformly sampling from. And we know that a large fraction of them will have the desired lambda. Exactly because we know that the probability that when we sample from here, from this distribution, our lambda is going to be large, so a large fraction will have the property we desire, and so we just have to run through all of them until we find the one we want. Good. So this is our idea, but there's a problem. And the problem is that we need a lot of independence. So like our value of k, which is how many sort of like, remember from the definition of sequences of uniform bits, the amount of randomness, the amount of like the number of bits we can extract and sort of multiply and want them to be sort of independent. The amount of bits that we need, and the size of k, has to be about log n. And I told you to ignore these poly thingies, but the point is that the runtime and the cardinality. Yeah, question.
Why do you need log n?
It's complicated. I'm going to skip that. But the point is that if you look at the proof of this thing over here, of this. This theorem is very complicated, by the way. It's a fairly large paper. But when you sort of deconstruct this paper and look at the amount of randomness that it uses, you see that you only need either like bound sort of expectations of products of k elements of our permutations, or something like a similar thing, but instead of it's basically what you need this thing. We only need to look at these expectations of products of k variables.
Is it reasonable to say the following? Like if you look at the adjacency matrix of G, then lambda can be approximated by like some log n degree polynomial of entries of A, because you can take powers of A and like trace of some log n power of A would kind of approximate lambda?
Yeah, I guess that's kind of the point, yeah.
Okay. And then that's
some
log
like
n degree polynomial?
Yeah, there's some like other like technical details that are hard to explain. Like as I said, this is a very complicated long paper. But the point is that even if you don't understand the result, if you look at the things that the theorems they prove, you conclude that you only need log n y's independence. Okay. So the problem here is that this requires a lot of time, which is we don't have n to the log n time. We need polynomial time. Okay, so this is a problem. And to fix this, I'm going to change gears again. And this is how we fix it. And the way we fix it is sort of we use a different sort of model of randomness, I guess. And instead of sort of de-randomizing this in one shot, we're going to try to do this step by step. Let's see what this means. I'm going to define this thing called a lifting of the graph. This is also like a very common notion in Ramanujan graphs and this kind of stuff. And so the idea, let's say we have some edge. And now a 2-lift of this edge is going to be the following. We copy each vertex, so we get 2 copies of the vertex. And now we either place 2 parallel edges or 2 crossing edges between these. So these 2 graphs, this is a graph that is the 2-lift of this edge, or this edge graph. And this is also a 2-lift of this graph. These are the only 2 lifts of this graph. And I'm also going to associate like a plus and a minus to these things. So if I am, this edge is going to be 2-lifted by a plus, then I'm going to create these 2 copies and then parallel edges between them. And if I associate a minus with this graph, with this edge, then I'm going to create these 2 copies and cross the edges between them. Okay. So now we can basically extend this definition to a whole graph. And if you have like, let's say like this line of length 3 or length 2, we can do the same thing. We have copy each vertex and then either place parallel edges or crossing edges. So there's 4 different possible 2-lifts of this graph, depending on like if we cross edges here and we have 2 parallel edges here, or a cross edge here and cross edge here, and so on and so forth. Okay. And so, for example, for the sign pattern, plus and minus, the two lift that corresponds to this graph is this thing. We have the two copies, and then now plus, so we place two parallel edges over here, and a minus, so we place two crossing edges over here. So this indicates that there's this bijection between these two lifts and edge signings of a graph. And there's actually this very interesting theorem, that, or lemma, whatever you want to call it, that says the following. Let's say you have some graph. This is some original graph, G, or with a JC matrix A0. And now let's let's pick some signs, minus, plus, so on, and call this AS. And this is the two-lifted graph of the two-lift of this graph using this edge sign pattern. And now we can show that the eigenvalue set of A is equal to the union, or this multiset of the eigenvalues of A, is equal to the union of this multiset of eigenvalues of A0 with the eigenvalues of AS. The proof is very simple. I'm not going to go over it, but I just want to show you that basically 3 lines proves this thing. Okay. So why is this super important? I wanted to understand this fact. This is, I guess, the most important fact here is that if we look at the eigenvalues of the signing of our graph, the eigenvalues of the two left of our graph are basically adding these new eigenvalues. Question?
So when you're looking at the eigenvalues of the sign graph, in the adjacency matrix, are you also flipping edges according to the sign?
Yes. So we look at the adjacency matrix, and instead of having a 1, if there's an edge in V, we have a plus or minus 1, depending on the sign of that edge. Another question?
Yeah, in your previous example, after you did the lift, the graph became disconnected. So this.
Yeah, that can happen, but this is oops, wrong way. Yeah, that can happen, but this is a very simple graph. That won't happen if you have large enough graphs. But that's a good point, yes.
Pedro, can I ask
Yes.
you one quick
Yeah,
question? Let's say I was happy with the quasi-polynomial algorithm.
Mhm.
Then is it kind of easy to prove from Friedman that
Yes.
login? Okay,
Yeah,
just because
we'd be basically done. Yes, the thing I just said.
was that result known before?
It was, I think it was known, but it was not really published because but it was known.
Cool.
Okay, so the reason I'm telling you about all these two lifts is now recall that our main thing is to construct this magical graph with this nice property. Now, what happens is that if we have this, let's say we have some optimistic theorem that when we two lift a graph uniformly at random, the this is the spectral radius, so this is the maximum eigenvalue. This is what I mean by rho of A. So the maximum eigenvalue of this is actually not too large. It's actually basically your nice magical number times some small thing. If this is the case, recall that we're adding all these eigenvalues to our original graph. So we're doubling the size of our graph while maintaining good spectral expansion properties of our graph. So if this nice theorem is true, then we have this optimistic blend. Let's start with a small Ramanujan graph. And I'm not going to prove it, but it's KD plus 1, so a clay of D plus 1 at vertices is a good Ramanujan graph. And now let's say we apply this optimistic theorem, and we double the size of our graph, but we keep the nice spectral properties of our graph. And now we just do it a bunch of times until we have a graph of about n vertices. If this optimistic theorem were true, we'd be done. We'd have our result. So again, the point is we'd start with a small graph, and we use this theorem to say that if uniformly at random sign our graph, we don't get the eigenvalues of our sign graph are not too are good enough. Whenever we two-lift the graph using this sign pattern, we're just adding these new eigenvalues to our original graph. And if we keep doing this, then we keep finding good signings of our graph, then we'll be done. Because we'll always be increasing the size of our graph until we get something good. Question?
Possibly I missed something. Why would it be done? You still have problems with the magic random.
Yeah, we'll be done. I mean, this is an optimistic theorem, and I'm not saying everything. But we'll be done if you could de-randomize this theorem, of course. Yeah. So if we could de-randomize this using, for example, the pseudo-random sequence of uniform bits that I mentioned, then we'd be done. So this is our optimistic theorem. Unfortunately, this theorem is false. This does not work because this is not true. And we can actually prove something like this, but instead of getting this magical number, you get something like d to the 2/3. This was proved by William and Lineal in 2006. They introduced these nice ideas of two-lifting graphs to get something almost Ramanujan, but unfortunately this theorem is not good enough to get exactly what we want. But actually, what we have is, if we have this weird notion of bicycle freeness. And I know I'm introducing a lot of keywords and a lot of things, but this is going to be the last one. And bicycle freeness is very simple. Basically, if a graph is bicycle free at a radius r for all vertices, a graph is bicycle free at radius r, if for all vertices v, when you look at like a ball of radius r, so like all vertices of distance at most r from v, we find at most one cycle in this sort of subgraph induced by this ball. If this is the case, our graph is bicycle free. And now why am I talking about this? Because our optimistic theorem is actually true if our graph, our starting graph, is bicycle free at some like nice radius. And this is our key theorem from our proof. This is what we prove. And the key ideas are a lot of sort of heavy tools in this kind of stuff. There's this very well-known method called the trace method, which basically converts our problem from an algebraic problem to a combinatorial problem of counting closed walks in our graph. We actually consider some non-backtracking walks of our graph. We analyze, this is, in the end, this means analyze this quantity of like the trace of this non-backtracking matrix to some powers. And then like we use bicycle freeness somehow. And in the end, like we can de-randomize this using some k delta ky uniform bits with k about log n. And like, of course, I don't expect you to understand a proof using this. I'm just sort of going over like the main ideas or the main tools that we use. And I guess the key important thing is we need to be careful here because we want to make sure that the amount of like k wiseness or like we need k to be small enough for our thing to work. Because recall that we can only build these ky's, delta ky's uniform sets of bits. This is a reminder of like that weird property that I mentioned before. So this means that, yeah. And we need k to be small enough so that our construction, the size of the cardinality of our sets, and the time we need to construct them is small enough. And just so happens that by using these and leveraging these things properly, we can get this with some nice wise uniformness, and then we can prove this optimistic theorem, this actual theorem, not optimistic now, and we can de-randomize this theorem. And so in the end, like, what's your actual theorem? So, yeah, question?
Yeah. When you take a lift of a graph which is bicycle free at that radius, you're going to get a graph which is bicycle free at the same radius, but
yes.
the n will change.
Yes, n will be double.
So, I mean, at some point, so if you start with a graph of fixed bicycle free radius, eventually you will finish will not hold once your n is large enough.
Exactly. But we'll see how we deal with that. It's actually not very hard to deal with that. But now, let me just say what's the plan here and sort of revisit what you just said. The point is, if we start with a small graph with a very large bicycle freeness, basically large enough that we don't need it to increase, so we'll be big enough to hold for all of our graphs, for all of our lifts. And then we just do the same thing. We start with a large graph, a small graph, large bicycle freeness, good lambda. We find a good two-lift using our actual theorem, repeat a bunch of times, and then move around. So the only thing we have left is we have to find this nice small initial graph with a very large bicycle freeness, so we don't need it to increase overall. And we do that by using this theorem from before that I just tried to re-randomize in one shot and I couldn't, because I've actually been hiding something for you. You also get this graph G's bicycle free radius log n with high probability. So the same theorem also gets this thing. And so in the end, recall that you can re-randomize them using you need a log n and y's independence. That's too much time, n to the log n time, that's too much. So, but we have our two-lift theorem, so we only need a small graph. So what we do is, we generate a graph G using this thing, with 2 to the root of log n vertices. And now, if we plug 2 to the root of log n here, our time is actually polynomial. And now, because of this property that I said before, that the G is bicycle free with this radius, well, this means that 2 to the root log n has root log n bicycle freeness. And recall that we only need log n squared bicycle freeness. This is much larger than that. And this whole thing only requires polynomial time, and so we'll be done. Let me show you a proof picture of the thing that I just said sort of to end the talk. So the idea is that we use that theorem to generate this smallish graph with 2 to the root of log n vertices, with both good lambda, good spectral expansion, and also high bicycle freeness. We find a good two-lift using our actual theorem because we have high bicycle freeness, and so we can find a good two-lift. And we increase the number of vertices by a factor of 2. Repeat that about log n times until we have about n vertices in total, and we're done. We have our final graph with good lambda, 2 root t minus 1, plus something small. This all runs in polynomial time, and the number of vertices that we need is going to be about n. This is our end goal, and this is how we do it. And so to conclude my talk, I just want to say that the key takeaway is this, I guess this sort of recurring idea in like whenever you're sort of de-randomizing or sort of trying to construct some pseudo-random objects, a lot of the times it's very hard to de-randomize it like a random theorem in one shot. Like that's what we tried initially, it doesn't work. But if you sort of do it in steps, by trying to slowly progress somehow, by keeping some nice property and like increasing the size of your object or something, somehow magically they can actually make this work. So this is the idea. You start with a small graph using that weak theoremization of that theorem that I mentioned, with a small size, good bicycle freeness, good lambda, find a good two-lift using our actual theorem that we proved, repeat this a bunch of times, and in the end we have like a graph with this nice Ramanujan, almost or near-Ramanujan property. And I guess that's it. Thank you very much. If anyone has more questions?
So suppose I let you use random. Can you do better than choosing a uniformly random irregular graph? I still want you to do it efficiently.
Yeah, I guess that's a question that we didn't really explore. We explore like just slightly in one part of our paper, but not so much. That's a good question. I guess you could try to like show existence of these things. I don't think that's going to work because I'm not entirely sure about this, but I think there's this result that sort of says that. So like you know how like with high probability that theorem that I showed you a bunch of times. Let's see if I can find it here. Basically, the high probability graph, the uniformly random irregular graph has this nice property. But like, if you want to like sort of see how like all likely is it to have a graph with this thing, with like removing this factor with like something smaller than 2 root t minus 1, the amount of graphs that have this property is very small. You will.
I mean, I don't mean necessarily getting all the way down to 2 root t minus 1, but just beating the can you do anything to beat the uniformly random? Like, is there anything you can do that's better?
What do you mean?
D minus 1 prime,
Well, no, but it's still efficient.
Can you get
that was efficient.
Okay, so I didn't know.
Maybe we can take the questions offline now. So let's thank Pedro again.